Good evening, all. We'll start for the day. Session, sir, you can take over the class.
Sure, ma'am. I'll start. Yeah. So, good evening, everyone. Welcome to the 10th day of our session. So, let us discuss the concept of SVM today. Okay. Support vector machines. It's okay. Fine. Okay, fine, Purva. Yeah, I'll share. Right. So, let me just share the screen. Just give me a minute. Hold on. Yeah. So ma'am has actually shared the data set link. Okay. So just before that, we'll just discuss the concept first, and then we'll go into the project. Okay. So I'll make it quick. Let me share the screen. Okay. Okay. Fine. So let us start the today's session. Right. The concept for today is on SVM. Okay. So let us discuss first what is SVM and why we use SVM, right? And then let us go into a project, right? Some different project where even in space research and these kinds of things also we can use these machine learning algorithms to showcase that and to make you to understand how it is widely used into different sectors. For that, I've taken a very different project, which we can do it in by using SVM. Okay. Right. So let us start first by understanding what is SVM. So SVM, I would say in one word, in a short way, if I want to tell what is SVM, is basically SVM is a algorithm particularly used for both classification and regression. Okay. So it is one of the fewer algorithms which can do both classification and regression. But mostly, I would say, mostly, okay, in most of the cases, this is not like 100% I'm telling that. Mostly, in most of the cases, I would say, for, sorry, in most of the cases, I would say it is basically used uh, for classification problems because SVMs are very good when it comes to classification problems. Like very good means very good. There I can say excellent, right? Very good is a very small word. So they're very excellent, in the way they actually detect the classification problems. Okay. So this is the brief introduction about what is SVM. So let us dive deep into what happens. What happens in basically SVM, how to understand support vector machines. Let us understand. Okay. Right. So now let us first understand how it start, right? How it started. So it is a very, very, I can say very older algorithm, right? So basically the original algorithm of SVM was actually developed in the 1960s. So such a, older algorithm it is. The base for that algorithm has started in the 1960s, right? Where they started drawing a hyperplane. So when we little go further, I'll tell you what is a hyperplane and why the word hyperplane is actually mentioned in the concept of SVM. Okay, and after that, slowly advancements has happened. In the field of machine learning in the 80s, 90s, and so on, right? And in the 2000 when it came, it has become more popular, right? And people have done a lot of research. Okay, I've mentioned some history. Okay, just wanted to tell you, because this is one of the oldest algorithms which are actually existing in the machine learning things. Okay, right. And basically, if you ask me that, what makes SVM so special is its ability to handle both, I can say, linear and non-linear data, right? So basically, it can handle linear and non-linear data. And one more very interesting aspect is it can handle higher dimensional data, right? So if the data has three dimension, four dimension, five dimension kind of data also, support vector machines actually handle it, right? So in that way, even SVMs are very popular. They're very popular, and I would say they are very efficient as well. Okay. Now let me go a little forward in understanding the terminology in SVM. Okay. So there are few things which you need to understand, which you have to keep in mind when we talk about SVM. Okay. So the first very important thing is the hyperplane. Okay. Hyperplane is a very important word when we talk about SVM. So what is exactly hyperplane is? Hyperplane is nothing but a boundary. Okay. So let me just show you the a diagram. Okay. Yeah, just we can discuss based on the diagram. So it will be very easy for you also to understand. So here, if you see what exactly is hyperplane? Hyperplane is a boundary. Okay. So what is this hyperplane doing is, this is basically lying in the data points, or when we actually plot the data on the graph, that it is lying in the middle to do what? It is there in the diagram to divide the data points, right? So for example, when we have seen the logistic regression, right? So you have seen, a threshold value which is 0.5 in the middle. So like that, we don't have, a particular point like that, but we try to build a hyperplane when it comes to SVM. Okay. So there are different kinds of SVM, how to deal with it and all. I'll just explain, okay, in this project as well. So in the implementation part, so you'll come to know about the whole picture of SVM. Okay, so now you can see that there's a particular line called as a separating line. So that particular line is basically called as a hyperplane. So what is this hyperplane actually doing in the graph is, it is dividing the data points. For example, the points to the right hand side, right, or our right hand side, or left hand side of the line are basically the yes constraints on the to the left hand side, our left hand side, and right hand side of the line are basically the no constraints. So what is exactly it is doing is, it is dividing or segregating the data points into yes and no category, because we are talking about classification. So it is trying to do the classification. So it is trying to segregate the yes points and the no points, or you can say two different classifications. Now, the most important thing after that to understand, the first point is the hyperplane. Okay. So we build a hyperplane. Okay, fine. And now, if there is a, we also build a certain thing called as margins. Okay. Now, why do we build margins? Right? Because when we actually build a hyperplane is just a line. Fine. So why the concept of margin is coming in is, margin is actually helping the hyperplane. It is like, creating a, I can say a particular boundary near to the hyperplane. So what this does is, if a particular point is very close to that of the hyperplane, right? So which category we have to give? Either we have to give yes or we have to give no. Because of this, what are happening is, the misclassifications are actually happening, right? So further research has been done, and once they identified that this hyperplane can divide in the support vector machines, the next important thing came into existence is the margin. So what does this margin actually do is, this will actually create like a shield to the hyperplane. So this will allow that, whatever comes to near to this point, on this point, right? You can see here, right? Blue points is the no category, and the black points are the yes category. So whatever, they're supposed to come only near that margin only, right? And this hyperplane will be in the middle of the particular margins on both the sides. right? So something comes between that, a margin and the hyperplane is called as a misclassification. So we are not able to 100% predict that, which category we have to give that particular data point. Okay, so that is the reason we have built that particular margin, right? When we, build a hyperplane. That is one more concept which we have to understand. Now, another concept is the concept of support vectors. So there are something called as a support vectors. So the particular data points which fall on that particular margin of the hyperplane are basically called as a support vectors. So whatever falls on that particular margin exactly are basically called as a support vectors. So it is very important to understand what is a margin, hyperplane, and a support vectors when it comes to support vector machines, because our algorithm itself is called as support vector machines. Okay, so this is what I have mentioned here. Okay, you can just go through this later. So, I've shown the diagram and I've explained because this is the easiest way to understand. Okay, right. So now let us go a little forward. Okay, so now let us understand that how hyperplanes are actually built. Okay, now, the first important point is, how we generate a particular hyperplanes and we try to segregate. This is a very tricky, and a very important concept when it comes to the scenario of a hyperplane. Now, because this hyperplane is not just a hyperplane, it is, not just a line. It is a plane which is, dividing the classification points. So, it is basically dividing two classes, right? So it is very important for us to understand that, whether the data point is, whether it is classifying correctly, or we have built in such a way that the data point is, being classified correctly or not. So this doesn't stop here, right? So when we talk about the margin also, it is very important that, our margin is actually built in a, or you can say the margin is built in such a way that it is maximized, right? So it is maximized in such a way that the points, it doesn't come into that, margin of, what I've shown you, which is the, the line of the margin and the hyperplane. So the point doesn't, come here. Okay, so because, if it comes in the middle, right, so it is considered as a misclassification because we are not able to predict correctly. So that is what our talent lies, or our knowledge of, data science and machine learning lies when we do this SVM algorithm, that how we build that particular hyperplane. Okay, so that is what we are going to understand, and that is how we are going to do the classification using the SVM algorithm. So now if we go a little further, so this is a small a diagram which is, I hope, it is easily understood for you. There's a little, geometry part and, a little geometry, and, how do you talk about the boundaries, decision boundaries and all, that is exactly built. And how do we rotate a particular line, and, how based on that we are going to build a margin. So it's a small example of how, it can be built. Okay, so, if you have some mathematical background and all, you might understand a little, right? So what is the most important thing is, the hyperplane has to be, just remember in this a very easy sense. So hyperplane should be in such a way, right? The margin is dependent upon the hyperplane, right? So since the margin is dependent upon the hyperplane, it is very also, very key to understand that the points doesn't misclassify. Okay, so on that basis, we have to, build the decision boundary, because the margins and the hyperplanes are nothing but the decision boundaries. So it is where we are going to take a decision whether that particular point is a category of a true or false, or yes or no, or one or zero category, right? Now, let us go forward to understanding one more very important concept in the one very important concept in the SVM, which is the concept of kernel trick. Okay, just give me a minute. Now, right. So let us now understand that what is kernel first. Okay, because to understand kernel, or you know why we have to understand kernel is the whole SVM is actually dependent upon the concept of kernel. Now, let us see what is this kernel, right? So kernel is nothing but something, or I can say in a very simple language, kernel is a particular function. Okay, so even I've mentioned a very simple language, so that it is very easy to understand as well. So basically, kernel is a function which maps to the higher dimension. That's it only. Now here, if you see that if your value of x is less than or equal to 1, it becomes the output becomes 1, and if it is otherwise, it becomes 0. Okay, so this is what the kernel function actually does. Okay, now apart from the mathematical formulation, okay, so what does this kernel actually how does this kernel actually work into the reality, right? So that is what we have to understand. So this is a function, okay, because we already know that machine learning itself works on the mathematical and statistical functions. Great. Now, this, what does it do basically is it actually transforms the lower dimension data to the higher dimension data. This is what the first thing what the kernel does. Why we are calling it as a kernel trick is that after converting from the lower dimension to the higher dimension, right, how much of correct mapping it is able to do in the higher dimension. So whether it is able to create that data separability or the classification correctly when it is in the higher dimension. So based on that, it is called as a kernel trick. Okay, so now let us go forward, right? And let us understand even more what are the types of kernels what we have inside the SVM. Okay, so the first important thing is the linear kernel. Then we have the polynomial kernel. Then we have the RBF, which is the radial basis function. And then after that, we have the sigmoid kernel. So these are the four kernel functions which are popularly or which are used basically in the SVM, or which are highly used inside the, or SVM is built upon these four kernels. Okay, so you can think of like SVM is built upon these four kernels. Now let us see, let us keep it very short and try and understand that what is this linear kernel first. Okay, now as the name itself tells you, right, a kernel which is having a linearity, right? So linearity is nothing but something can be classified in a straight line. That is called as a linearity. So something which can be classified as a single line and which can be drawn as a single line, that is basically called as a kernel, right? Linear kernel, right? So this is one of the mostly used, right? One of the mostly used kernels, or one of the mostly used functions inside the SVM. So here I mentioned also where the linear kernel is basically used. So it is mostly used for the text classifications, because SVM application is not just in machine learning. It also extends its uh, functions and its usage into the NLP and deep learning as well in the AI implementation of AI. So that is why understanding SVM is very important, because in text classification or text mining or natural language processing, we are going to use a certain algorithms which are implemented in machine learning. Right? One of them is SVM. Okay. So now let us just see the diagram for what is a linear kernel. Okay. So this is just a small example for a two-dimensional data. Now, let us go to the next part, which is the polynomial kernel. Okay, so polynomial kernel is nothing but which is very similar, or we can say it is simple language what to tell is you would have heard about the word polynomials, right? So in mathematical terminology, you would have heard about the word polynomials, right? So you have one degree polynomial, 2 degree polynomial, 3 degree polynomial, right? So this degree of polynomial is what the d value inside the polynomial kernel. Right here, if you have 2, it is a quadratic, right? So the most common degree we are using is 2. Okay. So now, we don't use much of a degree because that also very key points I've mentioned in this project, because just want to keep it simple as well, to make you to understand what is SVM and then move into the project part. So basically, even as I already told you, in NLP, a lot of applications of SVM are actually there, right? So this is a polynomial kernel, which where it is, that we know that, a particular concept of polynomial. Okay, so this is the example where highest number of degrees, right? So one degree polynomial, 2 degree polynomial, and the fifth degree polynomial. So now let us go to the next function, which is the radial basis function. So this radial basis function, many people who would have seen this particular thing, this particular formula. If you have seen this, I can say normal distribution formula, you would have, just that bell would have rung, because this formula has been taken from this function is actually taken from the, a normal distribution. So here, it is basically the e power or the exponential of mod of uh, this is basically two lines you are seeing, right? So single line is a modulus, but if you see two lines, it's basically the inner product spaces. Okay, so you're going to use the inner product of x minus 5 square and then divided by 2 sigma square. So this is a basic function. So you need not by heart any formulas. So just you have to understand there is something called as a radial basis function. So this is basically based upon the normal distribution. So this is how the classification happens, right, when it comes to the radial basis. Okay, so this is how it's going to build the data points, and it is going how hyperplane and the support vectors you can see, right? And this is how the classification actually will be done. Okay, so now let us go to the fourth important kernel, which is the sigmoid kernel. So sigmoid kernel is basically used inside the neural networks. So this is how, again, you can see that it is used in the deep learning part. So that is why I told SVM will be used heavily in deep learning and NLP applications along with the machine learning applications. So it has that wide usage. It has that wide usage when it comes to the real world applications. Okay. Right. So So let me introduce you to the libraries, how we are going to use it in SVM. Okay. Sorry. Okay. So these are the libraries, right? So that was a short introduction. I feel that is more than enough for you to understand that what is SVM and what lies in the SVM. Okay. So something like the margins, hyperplanes, right? Support vectors. Then you have to know what is a kernel. Then you should be able to understand that there are four types of kernels, right? And based on this, the SVM applications are actually built, and for that we have different functions which we can implement. Okay, so these are some of the examples. This is how we are going to implement. Now let us go to the next part, which is the dataset information. Okay, so Map has shared the dataset with you in the chat. You can just check the chat. Yeah, you can just check the chat and you can download the dataset. So let me just first take the, let me just explain the data set first, and then I'll take the questions if you have any. Okay. So I'll give you 5 minutes so that you can give me, so you can ask me any questions if you have. Okay. So I'll just finish the concept, basic explanation of what is SVM. And let us first understand what is this data set, what we are talking about, right? So anyway, you have the data set with you. I'm not again, sharing the data set here, right? So, just go with the coding part. And first of all, I'll explain what is this data set. Okay. So this is a data set regarding the space. Okay. So many, would have, when you have seen the, word pulsar, you would have thought, Bajaj pulsar, right? So it is not. There is something called as a star, right? A particular neuron star, okay, or you can say neutron star, okay. So this neutron star is basically there is many stars which comes under neutrons, and one of the neutron star is pulsars. Okay, so why we are using this data set is this is one of the rarest type of star which is available, and this is it is also a kind of a star which actually gives you the radio emission. Okay, and it is actually related to Earth as well. So this is basically used in the scientific fields as well, right? So this is basically an interstellar space-time, interstellar medium, and the states of matter. So it's basically a star. You can remember like that. What is exactly we are trying to do with this data set is basically to understand whether here we have different kinds of columns, right? So for example, here, let me just take the data set and let me explain based on that. So here you can see that we have 9 columns in your data sets or features in your data set, right? So in that we have mean of the integrated profile and standard deviation of the integrated profile. So excess curtices, skewness, mean, right, and standard deviation, excess curtices, and skewness and class. So here this is this data set is little different from what you have actually seen. Okay, so here you can see that there are different kinds of data, right? Huge amount of data which is available. Now, what exactly or what is happening here is, so the amount of radio emission it is going to it is going to give, or the amount of the sounds it's going to make, or the amount of things what it is actually giving us, right? So based on that, or the certain kinds of particular aspects, we should classify whether that particular star is a negative, that particular star which is actually we are receiving the signals, or we are receiving that radio emission. Okay, so from any from that particular star, right, which are comes under this pulsars. So whether that particular star is actually a dangerous one or which is not dangerous for us. So we have to classify whether it is a positive case or a negative case. Okay, that is what this data set is actually about. This project is a very good example where we can identify that we can even use the our machine learning algorithms into the space technology or scientific technology as well. So right, so let us go to the importing of the libraries first, right? So let us try and understand first that what are the libraries we are going to import, right? And for models, let us start with the first. Yeah, we'll go in an order. So we are using the NumPy, Pandas, Matplotlib, and Seaborn, so that we already know, right? And apart from that, we are using the SVM metrics, right? So our SVM uh, our SVM algorithm will be actually in the sklearn library, right? So we have, we'll import from the sklearn.svm, and we import our our SVM as SVC. Okay, support vector classifier. SVC is nothing but the support vector classifier. Okay, so since it's a classification problem, the most the most you know the most used or the most important metrics which will be used inside the classification problem, you already know, because we have done some of the classification problems as well, right? So you can identify that what are the important data things which are you can be used in the classification. That is the right. So you would have known that some of the things like the I can say classification report, right, confusion matrix. Then we use the F1 score, uh, right? Then precision, recall, right? All these things which are the metrics we are going to use. So apart from that, since it's a support vector machines, the most important thing which should be also used here is the AUC and ROC curve. Okay, so this we'll also try to explore here, right? And we are also going to do the cross validations. We are going to use the k-fold cross validations in this project as well. So we are going to build different things. We are going to use the standard scalar because most of the data is a numerical data. Okay, so this is what our inputs or important libraries is basically about. And let us just first read the data set, right? So the data set, what I've shared with you, I have read it here. Okay, so I can see the data set which is actually there. So there are total of 17,898 rows and 9 columns are there inside the data set. Okay, so 9 columns and 17,898 rows or records are there in the data set. Okay, this is what the data set is basically about. Now, before I go into the EDA part and after that applying the support vector machines, let me take a few questions, right? So if you have any questions, you can ask me. So once that is done, I'll give just 5 minutes. So if you have anything, you can ask me. After that, we'll go with the project. Okay, it's a really, I can say there are a lot of things to be discussed in the project. Okay. So Purva, actually, the most important thing actually, how do we determine which model to use on the data set according to the business problem? Okay. So see, to be fair, okay, first of all, we should be able to identify whether, see, there is a small, very simple, I'll give you the answer in a very simple way. Okay. I'm not going to give some complicated answers. Okay, let us keep very simple. So what I'll tell you is in a simple way. First of all, we have to try to understand whether the outcome variable. Yeah, obviously we'll consider the business problem, right? That is very important. So without that, nobody plans data collection or nobody plans. Sorry. So nobody plans the data collection phase or the analysis phase and all. So that is very important. That I 100% agree. So we start by understanding the business problem first. Okay, that is acceptable. But the most important thing after that is, right? So first of all, we should understand or identify the target variable first. Okay. So it is very important to understand that which target, what is the target variable. Okay. So in that target variable, whether that particular target variable is coming under the classification or a regression problem. That obviously we have to identify, right? So once that is identified, whether it's a classification or a regression problem, and after that we have to do the EDA process and we have to identify, right, that whether it is a linear or a non-linear problem, right? So because we have different kinds of methods for linear and we have different kinds of methods for non-linear. So without identifying the whether it's a classification problem or a regression problem, and after that which kind of output, okay, let us say it is a classification problem. So, the variables are categorical variables, so the outcome is a categorical variable. So, the outcome is since it's a categorical, it comes under classification problem. Fine. Now, so since that is determined, we have to also identify that whether it is coming into a linear category or a non-linear category. Can a tree-based solution can be used? Okay, so how the variables, are they having multicollinearity? Like that, some preliminary checks we are going to do, and based on that, we are going to decide the machine learning algorithm what we are going to apply. For example, if we, do some checks like multicollinearity, remove the, whether the data is independent, we do multiple checks, right? So after doing that multiple checks, then maybe some three algorithms we have filtered it out. Let us say some three algorithms are there which will suit which actually met all our conditions. Okay. So now what we are going to do is we are going to use those three algorithms, and we are going to determine that which algorithm actually will suit our data set, because not every algorithm is going to suit our data set. So it is always, or you have to use the ensemble technique, or whether you have to use a single model, whether you have to use a multiple model technique. Uh, So mixing of multiple models like the ensemble techniques, so that we will decide on the nature of the data. So how the data is behaving, and whether it's a linear or non-linear category. Are there a lot of outliers in the data? Because some of the algorithms are not very good, when you have a lot of outliers. Sir, sometimes what happens is, you may say that, sir, we'll try to remove the outliers now, sir. Then why you are telling that, we that is also a factor. Sometimes we cannot process the data by removing the outliers also. At that particular phase, we cannot use the algorithms which can give you bad results when outliers are present. Sorry. So can give you bad results when the outliers are present. So in this way, we have to think, and based on that, we have to build that which algorithm suits based on our data cleaning process, preparation process, the importance of the variables, how they are contributing. If you have to cluster them, you have to cluster them. If you have to use a PCA, so all this process will be there when it comes to handling a huge amount of data for model building. So it's not a small thing. To build a model is very easy, but to build which model and to identify what is the correct approach, right? So that data cleaning and preparation phase is the toughest phase when it comes to the project deployment, building and project deployment in any project's life cycle, in particularly machine learning and deep learning. So that is the toughest phase, I would say, where you have to really work hard on that. When you to perfectly clean the data and build it in such a way that we can use the data for model building with a lot of confidence. So to come to that conclusion, that is a toughest thing possible, I can say. So that you have to experience. Okay, how much ever I explain, uh, so that you cannot feel that toughness. So when you experience it, you'll be able to understand the toughness in what I'm trying to tell you. So that is, I think I've given a very lengthy answer for your question. So yeah, it's a very interesting question, and it's a very good question because it's a practical question what you asked. Because that is the thing which will be running in the mind of many people. So how to, which model to choose, which model to build, which is a very good, how to determine which is good at what particular thing. And so yeah, it's like that. So any other important? Yes, so because so that's what. Thank you for giving that compliment. But personally, I would say you have to experience it to understand the best out of how to build a particular project when you're actually dealing with a real-time data set. So that's a tough thing to process, and tough thing to feel it. So anything apart from Purva's question, anything else you want to ask anybody? I think we crossed that 5 minutes also. So just let me know if you have anything, or else we'll just move on with the project. Yeah, actually, I've given to the coordinator. You can check. I'll make sure you get it. Okay. I've been sharing the files. Just give me a minute. Sure. Yeah, I've already shared. Okay, fine. I'll just reshare it. Okay. So that you can get it. Yeah. So just give me a minute. Think. Just give me a minute. I'll share it as well. Just share it again, guys. Just use them. Okay. So I've shared those five. You can just download those. So the today's one also I'll share. Okay. So I think you have got the link for the data set. So you'll be having that. So you can download the data set as well as the I'll share the IPYNB file as well. Okay. Fine. So that file you can import it into your Jupyter notebook and you can actually work on it. Okay. So you can also use it in Google Colab also. And you can work on Google Colab as well. Okay. Fine. Yes. Yeah. Fine. So let us go with the project part. Okay. Right. So we have seen the importing of the data set. I think after that I've stopped. Right. So let us go forward with the project. Okay. So let us try and finish off the project. Okay. The next thing is, let us go with the EDA process. Okay. So let us see the dimensions, right? So the shape is nothing but the number of rows and number of columns in the right in the data set. Okay. Now, right, and if you go to the head of the data set, which is just to check whether the data set is loaded properly or not. So I also told you that, right? And now after that, let us go to the next part where we try to identify that what are the column names. Okay. So the column names are whatever, right? This is there. So that particular name, whatever is in the data set, it is actually mentioned as the column names. Okay. So the mean of the integrated profile, standard deviation, and all those things. So whatever column names are there, it is going, we are actually giving that. Okay. Now let me go to the next part. Okay. And here I'm using this strip function, which is basically used to remove the spaces. Here you can see between the mean and the quote, there is a space, right? So these spaces can be removed by using the strip function. Okay. And here after removing that, you can see that when you print the column names, you can see that there is no space. Okay. This is just a small change what I have actually implemented. Now, since there is a lot of since there is a lot of names are really big, right? So what I'm trying to do is I'm just trying to rename that particular column. So integrated profile, I'm taking it as IP. So IP mean, and for integrated profile standard deviation, it is IPSD, and for IP Curtises, right? Then it is that IP skewness, right? And DM SNR mean standard deviation, Curtis's skewness, and the target class. Okay, so this is what we have actually changed it. Okay, so this is what we are trying to. We have changed it in a way that the column names have become little smaller. Okay, now let me go a little down. Here you can see that when I print the columns, you can see that the the names have actually changed. Okay. Fine. So this is what is basically about. So IP integrated profile and DMSNR is basically delta modulation. So that is the noise that it is about the noise, right? Which the that particular star makes. Okay. Now let us go to the next part and let us check how many we have actually, right? And we'll just see how many of value counts are there in the target class. Okay, so in the target class, we can see that there are zeros which are 16,259. Okay, and which actually here I have calculated the percentage. Okay, of the target variables. Okay, so in the in the target variables, the zero class, which is the -1, we are having 16,259. Okay, that is actually contributing to the 90% of the data. Okay, so around 91%, almost 90.8, right? So 98.8. So the others will be around 9.2 percentage. Okay, so more of negative and positive are very less. So only around some 9% of positive cases are there. So there is a lot of imbalance, right? There's a lot of imbalance in the data set. Okay, so how to handle that we will see in the coming thing. And let us go with the info of the data set. Okay, and in this data set you can see that there is no null values. Okay, 17,898 is the size which is there for the entire data set. So there is no problem of null values in this data set, right? And every value except the target class is a numerical value, right? Everything is a numerical value. The other eight columns, only the ninth column, which is the target variable, is the can say the everything is a value, even floating value. Yeah, even the target class actually is a, I can say it's actually a categorical. Okay, it is showing integer, but because we have given zeros and ones, it is showing as integer, but it is a categorical value. Okay, because it's basically a positive or a negative case. Okay, fine. Now let us go to the checking of the missing values. I think this one no need to explain, because when we sum the using the isNull function, we can see that whether there are null values or not. Okay, so you can see that there are no null values. Okay, so there is no problem of that. And now let us go to the yeah, this is what I just told you as well. 8 are continuous and one is a discrete variable. Okay, and okay, and in the missing, yes. So next, let us go to the describe function, where you can see that for the entire data set, right? You can see the mean value, the standard deviation, the minimum value, max, the 25th percentile, 50th percentile, which is the median value, and then the 75th percentile, which is the 25 percentile. 25 percentage is nothing but the first quarter, and 50 percentage is nothing but the second quarter, or you can say it as a median. And 75th percentile is nothing but the, or you can say 75th percentage or percentile, we can say as the third quarter, or you can say, yeah, you can say third quarter or 75th percentile, right? And for all the numerical values, and we have all the numerical values, just leaving out the target class, even though it is calculating, it doesn't make any sense because it is just zeros and ones. So now let us go forward, and let us, for all the 8 columns, let us, plot the box plots to identify the any outliers in the data set. Okay. So this is how we are going to identify, right? So there are a lot of outliers in the data set as well. Okay. In every column, we have some outliers. Okay. So you can see in the box plot that, something which is outside this box is basically is an outlier. So you can see a lot of black points which are outside the box plot. Okay. So something which is outside the box plot is basically an outlier, right? So okay, so which is outside the box plot is basically an outlier, and you can see a lot of black points outside that particular box plot. For every plot, you can see that there is a lot of points which are outside the box. So that indicates that there are a lot of outliers in the data, and my inference also confirms that there are a lot of outliers which I have mentioned here. So now let us try and understand that how to handle the outliers when we deal with the SPMs. Okay, so there are two kinds of ways to handle. So one is the first one is the hard margin variant, and the next is the soft margin variant. Okay, so there are two kinds of SVMs. One is the hard margin and the soft margin. And basically, the hard margins do not deal with the outliers. Soft margins are actually used for dealing with the outliers. Okay, so you can remember like this. Okay, so when you have outliers to apply the SVM, you cannot use the hard margin. You have to use the soft margin approach. Okay, so now let us go to the next very important thing is using a plots. Okay, let us construct a histogram. So what this histogram will actually help you to do is it will help you to check whether the data is skewed or not. Okay, whether the data is following a normal distribution or it is a skewed data set or not, that it is going to identify. Now, if you see that, if you just scroll it down, you can see that once the plot has been plotted, right? So subplots, if you plot the subplots, you can get it on the same line. You can see two plots in one box, so that can be done using the subplot function. Okay, so here we are creating bins. Okay, so defaultly we are taking some 2020 bins for building the histogram. So now once we have built that particular histogram, you can see that some are following normal distribution, some are a lot of skewness is there. So you can see this part is skewed, this is also skewed, this is also little skewness is there, this is also skewed is there, and this is there, this is there, this is there. So not much normally distributed things. And here my inference also confirms that we can see all the 8 continuous variables are skewed, right? So they're basically for not following the normal distribution, they are somewhat skewed. So what we have to do is now let us right. Now let us first try to implement the SVM part. Okay. Now what we'll try to do is, before training the algorithm, we are going to segregate the X variable and the Y variable. Right. So here you are segregating into X variable and Y variable. So here you can see that in the X, which are the independent variables, you need the entire data frame except one particular feature or the column, which is the target class, right? So except the target class, you need each and every, you need each and every, column inside the X, which is your independent variable. And in the y variable, you need only the target class, which is the dependent variable or the target variable, and you are taking and the y variable as a target class. So the next thing is using the four important thing, which is which you already know. The In that one is the x train, and we have the x test, x train, x test, y train, y test, right? And we use the function train underscore test underscore split for splitting the data set. Okay, so that we are going to use. So after that, we are going to give the test size as 0.2. Okay, and so if you're taking 0.2 as the test size, you can say that 80% is your training data. Now, if you see that, if you see the shape of the training and the testing data set, under the training part, you can see that you have 14,318 under the training part, and in the testing part you can see it is 3580. So it has divided into 80% and 20% of the data for training and testing, because we have given 0.2, which indicates we have given 0.2, which indicates the testing size is 20% and the training size is 80%. Okay. Now let us move forward. Now we let us apply the feature scaling. Okay, so we apply the feature scaling to the data set, right, to transform the data into a to make the data on the same page, right? So all the data points will be mapped between the points to from -1, I can say -3 to +3 if you are applying the normal distribution scaling part. So what we are trying to do is we are trying to do the feature scaling, and we are going to transform the variables in a easy convertible manner, which can be easily trained. Okay, so now let me go a little forward. Okay. Okay, so let us go with the first understanding of how to initiate, or how to build how to build first the SVM model or the support vector machine model. Okay. Now, the first one we are going to take is to predict the SVM. We are using the default parameters. We are not mentioning any one particular, for example, like a radial basis function, or the linear kernel. So here you can see. So right. So these are basically we are using the normal kernels. Okay, we are not using anything. After that, we are going with the different kernels, which you can see here. We are using the linear SVM, where the kernel is linear. So we will use that later. Okay. So before that, using that, we are doing with the normal hyperparameter, which is c is equal to 1.0. Okay. So here we are giving the c function. If you don't give the hyperparameter value as c is equal to, if you don't give as, if you don't give any c value, right, it basically takes the default as c is equal to 1. Okay. So if you want to apply this sigmoid function, linear function, and all those things, you have to particularly mention that. Okay. So so here, defaultly, the value of C it is going to take as 1.0, and it is going to take the kernel as RBF, which is the radial basis function. So it is going to train, and it is going to check the model accuracy by the default model parameters, which it is showing around 98%. Okay. Now, if we go to the next part, here instead of C is equal to 1, okay, So since we have a lot of outliers in the data set, we should increase the value of C, right? So higher C means fewer outliers. The value of C as higher C means fewer outliers. So I will run the SVM model with the C is equal to 100. So if I run my SVM model with C is equal to 100, even then I'm getting an accuracy of around 98% if you see clearly, right? So still we are getting an accuracy of around 98%. Okay. Now let me go to the next part where we are giving C as around 1000 now. Okay. So let us give the C as 1000. Now, even though we have run this support vector classifier model SVC, right? Here still you can see that your even though we have given the C as 1000, still we can see our model accuracy is around that same 98% what we have got before, right? Now, once we have run the default thing by giving C is equal to 1, which is the default one, and and the C value as 100 and the C value as 1000. These are nothing but the classifier values, right? To create a hyperplane. Now let us come to the next part. Where we start giving the kernels. Now here we have mentioned the first kernel, which is the linear kernel. Okay. Again, for the linear kernel, we will go with the default C value. Okay. So if for the linear kernel, if we go with the default C value, which is the default C value is 1.0. So we are getting an accuracy of around 98%. Okay. And again, if the same linear kernel, if we give the C value as 100, we are going to get an accuracy of around 98%. The same linear kernel, if we give the C as 1000, we are going to get the value as around 98%. So now, what did we observe, right? So we are observing a little higher accuracy if you are giving 100 and 1000. So see, it is basically 98%. In that 98%, it is showing 9816, 98309. So little better accuracy we can see, as compared to that C is equal to 1.0 in 100 and 1000. But that is not a great amount of difference that you can see. It's a very slight difference that you are able to see when it comes to the increase in the C value. Okay. Now, let us go to the next part of comparing the training and testing data. Okay. So here, when I predict the values of Y on which my X testing has been done. So I can see the values which are given here. Now, once the training part is done, we can see the training accuracy of the model, and the training accuracy is on the Y predicted values is the around 97%. That means, the testing was, on the X values, the testing was around some 98% and 98.32. Yeah. And for the, predicted values of Y, we are getting around some 97%. So ideally, if we see that both are very similar, right? So, they are very much comparable. That is what I've just mentioned, because the values are very much nearby. Okay, so let me check. I think I got a question. Okay. Okay, not a question. Fine. Okay. So now, I just mentioned here. So training score is around 97 and testing score is around 98%. So they're quite comparable and there is no problem of overfitting, because overfitting is something where training is done well and testing is not done. The accuracy of the testing gets a hit. So maybe, a training accuracy, you can see around some, 97% of training accuracy. And for testing, if you see around some 30% or 50% or 60% or 50%. So if you see something like that, it is basically taking a hit on the testing part. So if it takes a hit, you can say that, basically it is overfitting. But here, the training and testing are almost similar. So you can say that basically the data is actually not overfitting or underfitting. So there is no problem of both the things. Okay, now let us go to the value counts of the Y test. So for the value counts here at the top, you can see, when we went up, I'll just go back. Here you can see that it is a 3580, right? You remember that, right? So you have seen that it is around 3580, correct? So that is the value counts, and here you can see that in that value counts, right? Here we are checking the target class. In that we have zeros of 3306 and and for ones it is basically 274. Okay, so that is the, and we already we to check the value counts of how much of accuracy we are actually getting from the value counts, right? Null accuracy score. We are having a null accuracy score of around 92%. Okay, so our model's accuracy is around 98%, and our null accuracy score is basically around some 92%. So we are almost similar. It's above 90%. So the model is performing really well, or the classifier is basically performing really well. So that is what we can conclude from the analysis what we have actually done till now. Now, we have implemented the radial basis function, which is the default one with C value of 1 and C value of 100 and C value of 1000. After that, we have implemented the linear SVM with C value as 1, C value as 100 and C value as 1000. Now, let us go to the next part, which is the polynomial kernel. So in the polynomial kernel, we are going to give the kernel value as polynomial, and we are going to give the C value as 1, and we are going to train, and we are going to see the value as around 98%. And for polynomial kernel with C is equal to 100, you can see that the accuracy is around some 98% again. So little accuracy improvement has happened again, 98.07 and 98.24. Okay. So here, comparatively, it is giving little lesser result. Okay. I would not suggest, I should not have put this poor performance. It's not giving poor performance, but it is giving a little less performance, very little less performance compared to the linear one. Next, let us go with the sigmoid function with C 1.0. So if you here you are getting accuracy of 88%. So this is very less. This we can say poor compared to the other ones. So with C 100, you can see that you are getting an accuracy of around 88%. So this word is correct for polynomial kernel because sorry, this word is correct for the sigmoid kernel. Compared to even polynomial, the sigmoid is not good for this particular model. See, these four are part of SVM, but you can see when you do all the four, you can understand that here itself that sigmoid kernel is performing very badly compared to the polynomial kernel, and polynomial is doing little lesser compared to the other two kernels what we have. So that is how we are going to compare the models and trying to understand. Now, let us see the analysis of what we have done till now, right? So we are getting a good results when we have done the when we have done the SVM model using the RBF and the linear functions. So RBF is a radial basis function. So with C1000, okay. So basically we are achieving an accuracy of around 98.32%. So it is so here we can say right, the model is doing really well, I can say, but the problem is there is a lot of imbalance in the data, right? So that might cause little problem when we are actually trying to trying to predict the data points. So even though the building testing accuracy is fine, so it might be problem when we actually try to predict the completely unseen data. So for that, let us try and understand, and let us let us try to even more simplify. Okay, so let us even more simplify by implementing, let us see and understand that, how much predictions, how much of support and all we are having by, predicting or using the confusion matrix. Okay, because confusion matrix is a very good measure or a metric when it comes to the classification problems. So you already know that what is the confusion matrix. We already have, I've already explained and all. So I'm not going to touch this. Okay, so now I'm trying to predict the values of the confusion matrix, right? I'm going to build the confusion matrix for the y tested and the y predicted values. So once I build the confusion matrix here, I can see that the matrix is built like this. This interpretation of the result is very important. So the matrix has actually built 3289 true positive cases and 17 false positive cases and 44 of false negative cases and 230 of true negative cases. Now, so the always remember the true positive case and the true negative case divided by the total number will give you the accuracy. So here you can see when you calculate the accuracy, you are getting an accuracy of around, if you add them, you are getting 3519 correct predictions compared to that of 61 incorrect predictions in the data. So if you add, right, so this is how the confusion matrix actually looks, okay, when you plot it on the graph. So I'm just skipping this. I'm just going to the accuracy report. And if I, if I just check the accuracy report of the, where you have the precision recall F1 score, which is determined for the model. Here you can see that there is a, precision of 99% for zeros and 93% for ones, and a 99% for recall for zero and 84% for recall. So when you do the F1 score, basically the zeros are giving a better F1 score, and we have a better support also. So we have 3306 observations supporting that particular outcome what you have actually predicted. So compared to ones, which is 274, and your F1 score is basically around 0.88, okay, which is a little less compared to that of the zero predictions, which are which have high support. Then now let us go to the classification report, and here we have calculated the classification confusion matrix report. Here you can see that when you calculate, you are getting an accuracy of around 0.9830. So that gives you a classification error of around 0.170. Okay, so it might be a very less error, but 61 inaccurate predictions. So I can say there is somewhat incorrect predictions are still there because there is some error what is actually being predicted. So when you calculate precision, precision is actually giving a very good measure. If you see, you're getting a precision of around 99%, right? So that is what can be translated here also when you calculate the precision. So the formula will be a true positive divided by true positive plus false positive, where you can calculate the precision values. So recall, you're getting around some 98 or sensitivity. And for true positive case, you are getting around 98%. These are just formulas, substitution of formulas, which you have already got in the confusion matrix. So what we got in the confusion matrix, the same thing we are applying. So what we are applying, what we got in the confusion matrix only, individually I have put it so that when you actually practice also, you'll be able to understand that what we are trying to actually do. Okay, so that is what this part is actually about. And then we have calculated the false positive rate and the specificity and all those things. Okay, so we can calculate the F1 score. So this is already the things, these are some of the things which you already know because we have done this in the logistic regression, because logistic regression and even in the decision trees and random forest also we have done this, metrics, right? So you are aware of this particular metrics, what what we have done. The new thing what we have not done till now is the AUC and the ROC curve. Okay, so this is a little new, that what you have actually not seen in in our sessions till now. So what is this AUC and ROC curve, or you can say ROC and AUC curve is? ROC is basically the receiving operating characteristic, and AUC is nothing but area under the curve. Okay, I think I have mentioned here. Not mentioned, it is area. AUC full form is area under the curve. Okay, so these are basically diagrams, or you can say plots, right, which will actually try to predict this true positive rate and the false positive rate. Okay, so this true positive rate is basically called as the recall, and false positive rate is nothing but the ratio to calculate, right, to understand the true positive and false positive rates under one curve or one particular plot. In that case, this AUC and ROC curves are very important. Okay, so this is why we are going to plot this AUC and ROC curves. Okay, so now let us use this AUC and ROC curves and let us plot that, okay, on the graph. Okay, so you can see the ROC curve which has been plotted, right? So the ROC curve, and the function is basically the ROC curve, underscore curve. Okay, so for that, for that, we are using the y-test and the y-predicted value to plot the ROC curve. Okay, and the same thing we are using here to predict the AUC ROC curve also. For predicting the ROC, yeah, here I have mentioned area under the curve, which is the AUC curve. So for plotting this, we use the function ROC under AUC underscore score, right? And it will together plot. Okay, and for that we are doing the cross validation part. Okay, and we are going to predict the AUC ROC curves cross validation score. Okay, now this is done. After that, what we are trying to do here is we are going to shuffle the data points and we are going to apply the k-fold cross validations. Okay, so k-fold cross validations we are going to apply, and in this k-fold cross validations is basically about taking one particular point, keeping it for the prediction part, right? So here totally we are giving number of splits as 5, so it will train on the 4 and it will keep one split for the testing part, right? So for this cross validation we are applying for on the the cross validation we are applying for the linear kernel. Okay, here you can see that it has been applied for the linear kernel. Okay, and we are predicting the cross validation scores of the 5 splits what we have made. Okay, so you can see the cross validation scores for the 5 splits what we have given here. Number of splits is equal to 5. So the average of all the 5 scores is what we have taken it here. Okay, and we have the same thing we are applying here. We have applied for linear, right? We have applied here for linear. The same thing we are applying for the RBF kernel, which is the radial basis function. Okay, and for that we are actually trying to, same thing we are going to do. We are going to give the validations as 5, and we are going to take the average again of all the cross validations. Okay, so that is the other thing what we have done. After that, what we are trying to do is we are trying to understand that using this grid search, which is the optimizer, or I can say hyperparametric optimizer, right? So grid search CV is nothing but an hyperparametric optimizer, which is used for support vector machines. So we are trying to improve the the accuracy score for the SVM. Now, when we try to build using the grid search, we got a score of around 97.93%, I can say. Right? So that is what I have got. Now, using the grid search for testing score, right? I have got an accuracy of around 98.35%. Now the magic lies why this grid search has actually helped. Okay, so many would say that, sir, it is very minor change that has actually occurred, not a major change, not a major improvement, but still you can see some improvement that you can see. So it is 98.32 when you are actually tested it, and when you have actually when you have used this grid search CV, the score is around 98.35. So you can see that a 0.03 percentage of improvement in the score, right? So that is in where there's a slight improvement, right, in what we have actually done. Now, what exactly what we are trying to achieve by this is the conclusion part. There are a few things which we need to discuss, right, in the conclusion parts. So actually, there is a lot of outliers in the data set, right? So even though there are outliers in the data set, right, increasing the C value is limiting the outliers. That is one thing. And one more important thing is we are getting the maximum accuracy from the methods, that is linear and RBF, which is radial basis function. So our polynomial and the sigmoid function are not performing that well. Sigmoid is not performing well in this case. Polynomial is somewhat better. So actually, in predicting the class labels, our models has actually done really well. Okay, even though there is an imbalance in the data set. And when we have actually explored the confusion matrix part also, it has, there are 61 misclassifications, but still our model performed, somewhat better, I would say, in our classification points. And our AUC and ROC curve are, which is very close to 1 when we have plotted in the graph. So that basically indicates that our classifier has classified well. It did a good job in classifying. And when we have used the k-fold cross validations also, the that compared to linear kernel, it has not performed that well. Okay, so it didn't help the model's performance in a better way, I would say. But grid search actually helped us to obtain a very good, I would say, very good model performance compared to that of the, other things what we have actually done. So this is what our project is about. Okay, so I'll share this project as well. Okay, so that you can actually practice this as well. Okay, so let me download this and share this also now. Okay. So just give me a minute. Okay. So I've shared this as well. So you can just just give me a minute. So yeah, so I've shared that project also in the group. You can just so in the chat, you can just download that as well. So if you have any doubts, we have some 4 minutes left. So you can just come up with any doubts if you have. I'll just take up the questions. So by 9 exactly, we'll end the session if you don't have any doubts. So if you have, we'll just carry on with the doubts or we can end. So let me close the data set also. So tomorrow, I'm planning to cover the, mostly the project on XG Boost. So that is one part I just wanted to cover. Okay. Then let us cover on XG Boost, gradient descent boosting. And after that, let us go to the time series. So if XGBoost project is done quickly, so we can go to the time series part. I want to start the time series, and then we let us go to the deep learning also. So a couple of projects on deep learning, and then let us also do some of the projects. One project on NLP. So this is what the basic idea, because mostly I'm concentrating on the projects part, so that you will be able to figure it out how to, what happens in machine learning, how to implement that, and, just some plain theory. So that is what for SVM also I've kept it very very short. The theoretical part I've kept it very short. So just the what is hyperplane, what is what are the the different kinds of kernels, what is a margin, what are support vectors. Just very briefly, I've just given a very if you just search for SVM, you'll get a lot of theoretical concepts. So how it is implemented, how the formula works, all those things, a lot of things are there. But as a person who is implementing machine learning, just a basic idea would be sufficient unless and until you want to dig deep and you want to understand. So I would say, this based on, how much you want to learn. Okay. So as a data scientist or a, data analyst, how much you want to learn, that will define. So, the amount of concept you have to dig in deep and you want to learn. So it's completely up to the person how much you want to actually take. Right. So yeah, that's what what I planned also, the more focus ha. So I'll just tell you also, okay, I'll give some brief idea. Okay, maybe maybe on Friday session I'll give a little idea. Once let me complete this project on XG Boost and on the time series also, because those two are very important concepts when it comes to advanced machine learning. So let me complete those two projects, and Friday let me find some time, maybe half an hour I can just dedicate to explaining the capstone project, what we are going to do. Okay. Yeah. Yes. So I'll take some. I'll pull some time out, and we have to also discuss some of the interview questions also on. Yeah. So after random forest, we have not discussed actually. So we have to also discuss the interview questions also. So yeah, we'll try to segregate in whatever time we have, and what can what we can maximize and learn in the sessions. So Sushmita ma'am, we can wind up. It's 9, so we can.
Yeah, sure, sir. Thank you.
Yes, ma'am. Yes, ma'am.
So yeah, sir, we'll wind up for the day. We'll meet again by tomorrow at 7:30.
Yes.
Okay. Thank you, sir. Thank you so much for your valuable class. Yeah, thank you, students. We are winding up for the day. Thank you all for joining. We'll meet again by tomorrow at 7:30. Thank you all. Good night.